So let's continue the topic of summaries of data. So in this lecture we'll talk about measures of spread or dispersion. So whenever you see the term spread, it's synonymous with variation or dispersion or scattering. So whenever you see the dispersion of a set of reference variables to the variety that they exhibit, so they basically represent how variety, so what is the variety in the data that you are being given. So a measure of dispersion generally conveys information regarding the amount of variability present in a set of data. So if all the values are the same, then there is no dispersion. But if all the values are not all the same, then the dispersion is present in the data. So the amount of dispersion generally may be small, but the values, though different, are really close together. So when the values are close together, then the measure of the dispersion is low. So when the values are far apart, then the dispersion is large. So this is the idea behind the measures of spread or dispersion. Now, so the figure that you see here shows the frequency polygons of two populations that have the same mean. Notice that the actual mean of the diagram is the same. But the thing is, one is having a smaller spread, the other has a larger spread. So this difference in spread comes because both have different variability. So different variability. This variability is what causes one to spread more, so one to spread out, and the other to be spread less. So for example, the population A here in general is spread less, but the population B here is much more spread out. So if the values are too widely scattered, then the dispersion will be greater. That's a common phenomenon. So let's take a simple example of two cholesterol measurements. So two samples of cholesterol measurements on a given person using two methods. So one is an autoanalyzer method and the second is a microenzymatic measurement method. Now the figure here represents two different samples. So and both of them have the same arithmetic mean of 200 milligram per deciliter. So visually both samples appear really different, which means that the difference in lies in the greater variability or the spread of the methods relative to one method relative to the other method. So how do you say that one method is much more relative with the other method? Is to understand the idea behind the topic of dispersion. So notice that even though, so how do you say that this has a larger spread? Is because the one that you are comparing it to has a smaller spread. So understand that variability is a relative expression where the comparison of two different substances gets you the final product. There are many measures of dispersion, but we use a select few because these are generally the most commonly used measures of dispersion. So among them, the first one is the range. So there are several different measures that you can describe the variability, but why do we use the range is because it's the simplest of all those measures. So the range is basically the difference between the largest observation and the smallest observation in a given sample. So if you have, for example, x1, x2, x3 and so on and xn, among that you found a value xs, which is the smallest value, and xl, which is the largest value. Range is the difference between those two, xl minus xs. So if we denote range by r, so then that becomes xl minus xs. So let's take an example of this data here. In this data, the largest value is 4146 and the smallest value is 2069. So xl is 4146 and xs is 2069. So we know that the range is xl minus xs. So 4146 minus 2069, which gives you a total of 2077 grams. So notice that this range, what does it say is it explains the actual width of the entire data from the smallest point to the largest point, and it shows you how spread out the data is. For example, if the range is small, then the spread is small. If the range is really large, then the spread is really large, then the range will be larger. So this is the idea behind the concept of range. So let's take the first problem that we did. Here we have a same mean, but let's take the range here of the first one. So the smallest value XS is 177 milligram per deciliter, and XL is 226 milligrams per deciliter. So for the first one, let's say for R for auto analyzer is XL minus XS, which is 226 minus 177. Next, here 192 becomes XS and 209 becomes XL. So our microenzymatic method becomes XL minus XS. Here it becomes 209 minus 192. So the first value is 226 minus 177. That gives you a total of 49 milligram per deciliter. So the range has the same units as that of the observations. So microenzymatic is 209 minus 192. That gives you a value of 70 milligrams per deciliter. Notice that, meaning that between the first value and the last value there is a 49 unit difference, and between the first value and the last value in the second method there is a 17 unit difference, which means this second one has a smaller spread, and the first one has a larger spread. So remember that we are only talking about the spread of data here, so we do not have any other thing to mention by using range. So let's try the same thing again in this problem. So pause the video right here and try the problem and find out the range. So for your reference, the smallest value is 38 and the largest value is 66. So this becomes XS and 66 is XL. So try using the values and try to find out the answer. So why range? Why can't we use anything else? So range, the usefulness of range is generally limited. So the fact that it takes into account only two values causes it to be a poor measure of dispersion, because it does not consider the internal data. So which means that it does not consider any other data except the smallest value and the largest value. Next, the main advantage of range is the simplicity, because you can calculate it easily. So since the range you can express it as a single measure, imparts minimal information about a data set and therefore of limited use. So just by knowing the range you cannot actually know nothing much as per the data that is provided. So whenever you express a range as a number pair in which XS and XL are the smallest and, so it is often preferred to express the range as the number pair. So basically we write the smallest value and the largest value as a data set. Next, one main disadvantage of range is that it is very sensitive to extreme observations. For example, let's say if in a data set one of the values is 110 and the other values is 200, so the range between these two values is 90. But if the larger value became really large, for example 300, so the actual range becomes 190, which means that it's really very sensitive to extreme observations. So another main disadvantage of range is that it depends on the sample size. So the larger the n value, the larger the range. So because the more spread out the data, the more the range of the observations. So to combat that, we use the second one, the variance. So variance is a measure of dispersion that is relative to the scatter of the values above the mean. So it takes into account the mean and it takes into account how far the values are from the mean. So remember, variance observes how scattered the values are from the mean. But there is a common problem with mean. Notice that it takes into account the difference between the F's observation and the mean, but squares it and sums it up. So it takes into account the actual observations square value. So this is also called as a root mean square method, or the mean square variance. Notice that we are taking the mean and we are taking the difference mean standard deviation or the square standard deviation variance. So this idea is because, for example, let's say if you have a data of 1, 2, 0, -1 and -2, and if you want to find the standard deviation of this data, notice that 0 here is the actual value. But the problem here is that whenever you end up with the mean becomes 0. So fine, mean is 0. But what happens to the variance if you add up all the values? So because the values are not representative of the actual variance, so we use the root mean method. The root square method or this mean square method is mainly used because it can represent the actual scattered values of the data. So it can represent the actual scatter of the data. So the scatterer here uses S as the formula, S square equal to sigma xi minus x bar square by n minus 1. What does that mean? For example, let's say I have S square, let's say I have observations x1, x2, x3 and so on until xn, and the mean of these values is x bar. So taking into consideration the mean, so we get x1 minus x bar square plus x2 minus x bar square plus x3 minus x bar square plus and so on plus xn minus x bar square divided by, taking into total number of observations, n is here is the sample size, and we write n minus 1. This is the original formula. So to condense this, we write all these pluses in one single form. So we write S square equal to sigma I equal to 1 to n xi minus x bar whole square by n minus 1. So this is the condensed formula for the original formula. So by using this condensed formula, we can also write a little larger data values, and it helps in understanding how the data actually works. So with that in mind, now let's go into the variance part. So this here is called as the sample variance. Remember that this represents the sample variance. It's not the population, but it's the sample. Now the question comes back to one value called the degrees of freedom. So whenever we compute the variance, the reason we are dividing with n minus 1 rather than n is one of the theoretical considerations. We call it as the degrees of freedom. So n minus 1 is called the degree of freedom of the variance or the standard deviation. So when you take the actual deviation value is sigma n equal to 1 to n xi minus x bar by n. The reason for choosing n minus 1 is that the sum of deviations of individual observations of a sample about the sample mean is always 0. So when you take from the sample mean, if you take any observation values without squaring them, the problem with not squaring them results in the sample mean becoming always 0. Even though the actual mean is not 0, you end up with an actual sample mean of 0. So hence we always use n minus 1 values so that the nth one is determined automatically. So this might not sound correct, but this is how the actual method is done. So this is far above the actual syllabus of the course. So we'll try to use n minus 1 as the main value. Now, so let's take the data. So this is the age data of 10 subjects. Now, so they are asking you to calculate the standard deviation or the sample variance. So this is the data. So all of these are observations. So notice that write down each of them as the observations. You get x1, x2, x3, x4, x5, x6, x7, x8, x9 and x10. So there are a total of 10 observations. Now in these 10 observations, so the first thing, remember that the variance formula is sigma xi minus x bar whole square by n minus 1. So for simplicity, I have already calculated the x bar value, so we don't need to calculate. So x bar here is 56. Now using this x bar value, now we want to calculate the actual variance. So one way of doing this is by writing the values directly as the formula, but the way I recommend would be to write it as a table. So how to write the table method? So how do you write the table method? So write down the x bar value. So the first values that you want to write down is the observations xi. Second one is x bar. Third one is xi minus x bar. And fourth value is xi minus x bar square. That's it. Now write down the values for xi. Xi is the observation. So 43, 66, 61, 64, 65, 38, 59, 57, 57 and 50. So the x bar value is 56. So I'll write down all the values. Let me for all of them. So let's try and use. So try to use a calculator, don't do it manually. So let's take the first value 43 minus 56. So that gives you a negative 13. 66 minus 56, that gives you a value of 10. 61 minus 56, that gives you a value of 5. 64 minus 56, that gives you a value of 8. Next 65 minus 56, that gives you a value of 9. Next 38 minus 56, that gives you a value of negative 18. 59 minus 56, you get 3. 57 minus 56, 1, and then negative 6. So now we have all the values of xi minus x bar. Now we want to do the square. So take the value that you already have now here and square that value. So the square of this value. So minus 13 square becomes 169. Remember that minus becomes plus when you square it. So 10 square is 100. 5 square is 25. 8 square is 64. 9 square is 81. Minus 18 square is 324. 3 square is 9. 1 square is 1. 1 square is 1. Negative 6 square is 36. So now once you have all the values that you need, so we have all the values that you need. What I want you to do now is add all these values. So that is 169 plus 100 plus 25 plus 64 plus 81 plus 324 plus 9 plus 1 plus 1 plus 36. So this value of that sum is sigma xi minus x bar square. So that value is 810. Right, and look at the total number of observations. So you start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 10. So we want to have s square. S square is sigma xi minus x bar square by n minus 1. So which is 810 minus 10 minus 1. So that is 810 by 9. So 9 ones, 9 90s. So s square here gets a value of 90. Now once we have the value of s square, this here is the variance. So the variance is 90. So this is how you do or how you calculate the actual value of variance for any given problem. So you can see that there is an actual method that you can do, but this is too large. So if you reduce it into a table, it makes it easier. So first write down all the observations, next write down the mean value and subtract both of them and square both the values. So that ends up giving you the values. Remember that when you square, don't forget to change negative to positive, because that square of a value will never be negative. So this is the idea behind the topic here. Now, so let's continue the topic. Now let's find the variance of a population. So the variance of a sample is determined as S square. For a population, the parameter is sigma square. So sigma square is the exact same formula. So sigma square is sigma xi minus, remember that x bar is for the sample. So in place of x bar, we use mu. So xi minus mu square by, in place of n minus 1, we use uppercase n. So we know n minus 1 here. So n minus 1 only applies for the sample, not for the population. So here mu here is the population mean, capital N is the population size, sigma square is the finite population variance, and x is the sample values. Now, the next one is the value of standard deviation. So standard deviation is the square root of variance. So remember that square root of S square becomes S. So S represents the standard deviation. So the formula becomes S is equal to under root sigma xi minus x bar square by n minus 1. So this is the formula for the standard deviation. For example, if you look at the last problem that we did, the variance was 90. So taking into consideration the variance that we have, so if you take the value, if you want to find the value of S becomes square root of 90. So when you write 90, so square root of 90 becomes 9.4868. So this is the standard deviation for the problem. So standard deviation can be represented as SD or smaller case SD. So the standard deviation measures the dispersion or the spread about the mean. So for example, if you have a data set, so if this is the mean, standard deviation basically checks how far apart is the data from the mean. So this is how the standard deviation generally works. Now this brings up the question, so the bigger the value of standard deviation, the more variability in the data. So the standard deviation can equal 0 if there is no spread at all. The units of standard deviation are generally the same as the units of data, but it's not the same case for variance. Variance becomes the square of the original unit. So standard deviation is a much more clear representation of how variable the data is. So now, the same case we can write the standard deviation for the final population. So in place of sigma square, we have sigma equal to sigma square root of sigma square becomes square root of sigma xi minus mu square by uppercase n. So this is the formula for standard deviation of a finite population. Now, so let's take the original problem that we started with and let's try to calculate its standard deviation. So there are two methods here and we are trying to compare between the two methods. So let's take into consideration the first value. So in the first one, write down the observation. So let's start with auto analyzer method. So in auto analyzer method, so again the table stays the same, xi, x bar, xi minus x bar, xi minus x bar square. There is not much difference in the way we calculate it. So again 177, 193, push it a little up. $195, 209 and 226. So x bar is given, which is 200. So 200, 200, 200, 200, 200. So the first value is xi minus x bar is 177 minus 200. So which gives you negative 23. 193 minus 200 is negative 7. 195 minus 200 is negative 5. 209 minus 200 is 9. 226 minus 200 is 26. Now xi minus x bar square, so that becomes minus 23 square, so that is 529. Next 7 square is 49, minus 5 square is 25, 9 square is 81, 26 square is 676. So now we have the values. Now again the problem, again add all of these values, that gives you a value of sigma xi minus x bar square. So that value becomes, you have 529 plus 49 plus 25 plus 81 plus 676. So that gives you a final answer of 1360. So we have 1360. Now we want to calculate the standard deviation. So standard deviation is square root of sigma xi minus x bar square divided by n minus 1. Sorry. So n here is 5. So n minus 1 becomes 4. So square root of 1360 by 4. So 1360 by 4 is 340. So square root of 340 becomes 18.439. So yes, here is 18.439 milligrams per deciliter. So use the same method. Now try to calculate the standard deviation for the microenzymatic method. So pause the video right here and try to calculate the value for the microenzymatic method. So before that, I will write down the values. So x bar, xi and x bar. Xi is 192, 197, 200, 202, 209. So x bar again is 200, 200, 200, 200, 200. So pause the video and solve this problem. So let's try the next problem. So this one you can try it on your own, but it's a pretty large problem. So what I would recommend is, I would recommend you to try this on an Excel. So that would be the easiest one. So if not, just skip this problem or just do 10 observations. So try it on your own and try to calculate variance and try to calculate the standard deviation. Right. So let's go to the next concept, or the next measure of dispersion, the coefficient of variation. So the standard deviation in general is used as a measure of variation within a given data set. So when you have a single data set, it's easy. But when you want to compare the dispersion between two data sets, then because the two standard deviations are completely different from one another, it might lead to fallacious results. So it may be that the two variables involved are measured in different units. For example, if you wanted to compare, say for example, for a certain population, there is a serum cholesterol level, so measured in milligrams per 100 ml, or more variable than body weight measured in pounds. So to compare these two units, one is milligrams per 100 ml and the other is in pounds. So there is no actual way of measuring both these units standard deviation and compare the actual results that you end up with. So even with the same unit of measurement, for example, if the two means may be quite different, then that also creates the same problem. For example, let's say if you are trying to compare the weights of first grade children and trying to compare the weights of high school freshmen. So these are two much different data sets. Even though the actual unit is the same, you cannot have the same result of dispersion, because numerically trying to compare two different values from two different data sets is always a problem. So to make sure that we try to do that, so we use the coefficient of variation. So what is the coefficient of variation? So it is defined as the ratio of the standard deviation to the mean. So measured in a percentage, so we write it by times 100, so into coefficient of variation is measured as a percentage. So this measurement actually makes it relative, so that the variation becomes a single value for both of them. For all the values becomes a single unitless quantity. So because it becomes independent of the scale of measurement, so it makes it easier to compare this with anything else. So let's try this example. So there are two samples of human male yields, that yield of results that show in the table. So for that, so find that which is more variable. So they're asking you to find when weights of 25-year-olds on the weights of 11-year-olds. So 25-year-olds, the mean weight is 145 given, and 11-year-olds, the weight is 80 pounds, and they've given a standard deviation of 10 and 10. So let's calculate the CV for 25-year-olds. So that is standard deviation by mean. So the standard deviation here is 145. Sorry, the standard deviation is 10 over 145. And for CV for 11-year-olds, again standard deviation by, so standard deviation is 80 and standard deviation is 10 and weight is 80, x bar is 80, 10 by 80. Now to calculate these two values, so what do you get when for 10 by 25, 10 by 145? So that value is times 100, so that gives you a value of 6.896%. And for the CV of 11-year-olds, so 10 divided by 18 into 100, so that gives you a value of 12.5%. So notice that before, when you wanted to compare, you would have said that both of them have the same standard deviation, but in originality the actual coefficient of variation is much larger for 11-year-olds than that of 25-year-olds. So the 11-year-olds have a higher variation in the sample than that of 25-year-olds. So this is how we can calculate based on the data that is present. So use the same principle here, and for this data, so it's already mentioned that the standard deviation is 445.3 grams and x bar is 3166.9 grams. So use that data and try to find the coefficient of variation for this data. So pause the video and solve the problem. So let's continue on the next topic, percentiles. So percentiles are also called quantiles. So percentiles are a value based on a set of observations. So what we do here is we take the entire observations and we split it into 100 equal parts, whatever the number of observations are. So we split the observations into a set of 100 equal parts. So there are a total of 99 percentiles. Remember that 0 counts to 100. So we count from 1 percentile to 100 percentile. So that's a total of 99 percentiles. So percentiles in general are used to locate data on a horizontal axis. So why do we need percentiles is because percentiles have the advantage over the range, because it's less sensitive to the outliers, and it's not greatly being affected by the sample size, because sample size does not affect the way the percentile works. So how do we define a percentile? So given if you have n number of observations, so the pth percentile is pth percentile p is the value of x such that p% of values are less than p and 100 minus p% of values are greater than p. So let's take a simple example for that. Let's say I have a set of observations. Let's say I have a 50 percentile. So the 50 percentile value here, let's call it is 5. So which means that 50% of the values are less than 5. So 50% of values are less than 5 and 50% of values are greater than 5. For example, let's say if I want to take 60 percentile. So the 60% of value is, let's say, 6, which means that 60% of values are less than 6, and take out from 100% 60%, that's 40%. So 40% of values are greater than 6. So for example, let's say if somebody gets a 98 percentile in their exam, so not percent but percentile, it means that 98% of the students are less than that person, have marks less than that person, and only 2% of the students have marks above that person. So this is the idea behind that word percentile. Now we use subscripts on the p value to distinguish one percentile from another. For example, 10th percentile can be written as p underscore 10, and you write 70th percentile p 70, and so on. So what does 70 percentile mean here? There are 70% of the values that lie below the value, and while 30% of the values lie above the value of P70. So the 50th percentile is also the median, and we represent it as P50. So the median basically divides the lower 50% of values and higher 50% of values in a data set. So remember that 50 percentile is the median. So how do you find the percentile value? So the first thing that we have to do is write down the data in ascending order, which means that you are writing the values from the smallest to largest. So the pth percentile can be found as, so the pth percentile of any can be computed based on one condition. So the first condition that we require is NP by 100. So where N represents the sample size and P represents the percentile to be found. Remember that we don't need to write the percent, not the value as decimal, we have to write it as a number. So now once you find NP by 100, there are two conditions that we have to determine. If NP by 100 is an integer, or if NP by 100 is not an integer. So remember that we are using two values, if NP by 100 is an integer and if NP by 100 is not an integer. Now if NP by 100 is not an integer, so the value of NP by 100 so is taken. So for example, let's say consider that k is a value that equals NP by 100. So we are taking this NP by 100 value and we write it as the closest integer. So the closest integer's observation becomes the percentile. For example, let's say if NP by 100 is, let's say, 10.5, right? So let's say 10.55. So we are going to round it off and we'll always write the next integer rather than writing the previous integer, so which is about 11. So here the 11th observation in the order is the pth percentile. So this is how we take the integer value. Next, I'm sorry, this is the largest integer, actually less than the observation. So this is 10th observation. Now here the value should always be less than the actual, so the observation, so this value should always be less than the decimal value. So the closest integer less than the decimal value is the percentile value. Now what if NP by 100 is an integer? So if NP by 100 is an integer, it is the average of, so then we take two values, NP by 100 and NP by 100 plus 1. So the average of NP by 100 and NP by 100 plus 1 integer, sorry, NP by 100 observation is the percentile. Now this might sound a little bit confusing, so we'll do a problem so that you understand how percentile in general works. So before we do an example, let's talk about the different forms of percentiles. So there are three frequently used terms. One is quartiles, quintiles and deciles. Quartiles always represent quarters, so they are, you have to divide the data set into 4 equal parts, so that's 25th, 50th, 75th percentile. Quintiles divide it into 5 equal parts, that's 20th, 40th, 60th and 80th percentile. Deciles divide the data set into 10 equal parts, that's 10th, 20th, 30th and so on until 90th percentiles. Now let's take a given data set and let's try to find the actual values. So let's take an example of percentiles. So this is a data of GRF measurements when trotting of 20 dogs with a lame ligament. Now let's try and understand how percentiles work, and let's see the data. So let's check the total number of observations. So if you look at it, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's about 20 observations in total. Now let's consider that first we are finding the 20th percentile. So when you want to find the 20th percentile, so P becomes 20. So the first value that we want to find is NP by 100. So N is 20 into 20 divided by 100. So that becomes 0, 0 gone, so that becomes 4. So is an integer. So when you have when NP by 100 is an integer, we will have to take the average of NP by 100 and NP by 100 plus 1th observation. So what does that mean? NP by 100 value is 4, so 4th, and NP by 100 plus 1 becomes 5th observation. So we are taking the average of 4th and 5th observation. So what is the 4th observation here? So you have 4th observation, which is 27.0, and 5th observation, which is 27.2. So now P20 becomes the average of 27.0 plus 27.2 divided by 2. So that becomes 27.1. So the 20th percentile value here is 27.1. So this is how you can find the final answer. Now let's take a percentile that's much more complex. Let's say, for example, I'm trying to find the percentile of let's say I want to find the 25th percentile. So again, so P becomes 25. N here is 20. So let's find NP by 100. So NP by 100 becomes 20 into 25 divided by 100. So 25 ones, 25 fours, 4 ones, 4 fives. So this is 5th. So 5, the value is 5. So 5 is an integer, which means now NP by 100 becomes 5. So again, average of NP by 100 and NP by 100 plus 1th observation. So NP by 100 is 5th and 6th. So we are taking the average of 5th and 6th observation. So P25 becomes NP by 100, so is 5. So 5, 5th observation here is 27.2 and 6th observation is 27.4. So you get 27.2 plus 27.4 divided by 100. So that becomes 27.3. So the 25th percentile of this data is 27.3. So this is how you find the answer. Now let's take another example. Let's say I am finding an odd one. For example, let's say 55th observation. So 55th percentile. So 55th percentile, how do you find this? Now again, N becomes 20, P becomes 55. So we are finding NP by 100, so that becomes 20 into 55 by 100. So 20 ones, 20 fives. So 5 ones, 5 11s. So that is 11. So 11 here is an integer. So which means that we are going to take the average of NP by 100 and NP by 100 plus 1. If you don't want to write this, what you can do here is, if it's an integer, take the average of that observation and the next observation. So here 11 is the NP by 100 value, so take 11th and 12th observation. Here 11th is 31.5, 12th is 31.6. So we are taking P55 becomes the average of 31.5 plus 31.6 divided by 100. Sorry, divided by 2. So that becomes 31.55. So P55 is 31.55. So you can also try, for example, let's say a different type. For example, let's say I am finding the 92nd percentile. So 92 percentile. So P becomes again 92. N here is 20. So in this data now again, let's try and find the value. So we have to find NP by 100. So you have NP by 100, which becomes 92 into 20 divided by 100. So 21s, 25s. So we get 92 by 5. So which becomes 18.4. Now we cannot find the 18.4th observation. So this is not an integer. So what is the value then? So we have to find the integer less than 18.4. So the closest integer less than 18.4 is 18. So P92 becomes the 18th observation. So the 18th observation is 36.9. So that becomes 36.9. So this is P92. So this is an example where the actual value is not an integer. So understand how you can do all these data. So this is how you can do percentiles. So again, so in the same problem, try 75th percentile, try 90th percentile, and try 99th percentile. So and try all these values. So pause the video right here, use the above data. So notice that here n is 20. So and wherever you write p, use the percentile value itself. Right. So pause the video here and do the problem. So if you're done with the last problem, try this problem. So in this problem, first sort the data. So sort the data in ascending order. So second, they are asking you to find the 10th percentile and 90th percentile. So try this problem. So pause the video here and try to solve this problem. So if you're done with the last one, try another problem. Here also again, first sort the data in ascending order. Again, we don't need to read the I value, these are the values that you need. Right. Second, they are asking you to find the 20th percentile. Remember that here, take the value of n into consideration. N here is 9 and the p value will be 20. So try to find p20. So pause the video here and solve this problem. So next, let's talk about the other forms of measures of dispersion. So the first one again is, the next one is interquartile range. So the range that we use is a crude measure, meaning that it does not consider the variability of the data and it only takes into consideration the largest and the smallest value. So because it's a crude form of a measure, we do not have a sufficient way of measuring what the value of the range, what the range represents. So one another way of similar measure that reflects the actual variability among the middle 50% of the observations in a data is called the interquartile range. So interquartile range is given by Q3 minus Q1. Now what is Q3 and what is Q1? So remember the quartiles. So we talked about quartiles as there are three main quartiles, Q2, Q3 and Q1, Q2 and Q3 you're going to learn. So Q1 is the 25th percentile, Q2 is the 50th percentile and Q3 is the 75th percentile. 50th percentile is also the median, so represented by M. Right? So when we are calculating the interquartile range, what we are doing in this data is we are taking in the difference between Q3 minus Q1. So basically we are dividing, so we are subtracting 75th percentile and the 25th percentile. So this is the IQR, interquartile range. Why percentiles The reason mainly is because percentiles actually take into consideration the whole data. So one way of looking at interquartile range is the data of actual significance. So interquartile range shows you the data that's of actual significance because it focuses on the central 50% of data. So it focuses on the central 50% of the data of any given sample data. So this is how we find the interquartile range. So let's take an example. A larger interquartile range indicates that there is a large amount of variability among the middle 50%, and if you have a small interquartile range, it means there is a small amount of variability among the relevant observations. So it is more informative because to compare interquartile range with range for the entire data set, because interquartile range relies on the entire data, not on the edge values of a given data. So one way of comparing them is to take the ratio of the interquartile range to the range and multiplying it with 100. So it basically says how much of the range is the interquartile range occupying. So that is one another way, and the value, as the value goes closer and closer to 100, so IQR is a better representation of the entire data. So this is how we know the interquartile range advantages. So one other use of interquartile range is to know outliers. So outliers are extreme values. So they can be really small or really large. So in a given data set, these extreme values are called outliers, and to determine outliers we use the quartiles. So if the value of the observation is greater than Q3 plus 1.5 times IQR, or if X value is less than Q1 minus 1.5 times IQR, so then those observations are called outliers in any given data set. So this is how we determine the extreme values in any given data set. So let's take an example from the same data that we did in the last part. So here we are trying to find an outlier. So for the first thing that we need to do is we want to find Q1 and Q3. So remember that Q1 is 25th percentile and Q3 is 75th percentile. To make it easier, what we can do is, if n is an integer, so we can find the NP by 100 value again. So the same process as before, first find NP by 100. So NP by 100 for the first one becomes, there is 20 observations into 25 divided by 100. So 25 fours, so 4 fives. So is an integer. So remember that if it's an integer, we take the average of that observation and the next observation. So here we are taking the average of 5th and 6th observations. So to take the average of 5th and 6th observation here, so 5th observation here is 27.2, 6th observation is 27.4. So we takes 27.2 plus 27.4 divided by 2. So that becomes 27.3. So this is Q1. Next we want to find Q3. So to find Q3 again, use NP by 100. So that becomes 20 into 75 divided by 100. So once we find that, that value becomes 20 ones, 25s, so 5 ones, 5 ones and 5 fives. So that is 15. So is also an integer, which means that Q3, which is P75, is the average of 15th and 16th observation. So notice that this is 11, 12, 13, 14, 15. So 15th and 16th observation. So that is 33.3 plus 33.6 divided by 2. So that becomes 33.45, sorry, 33.5. I'm sorry for that. So that becomes a value of 33.5. 4. Right? So this is the value of 33.45. So give me a second, let me check the actual value. So yes, the value is 33.45. So now we have the two values that we need. Q1, which is 27.3, and Q3, which is 33.45. So we have the two values we need. So here we are trying to find the outliers. So we have to use the formula. So there are two outliers. If the x value is less than Q1 minus 1.5 times IQR, and Q greater than, Kx greater than Q3 plus 1.5 times IQR. So let's first find IQR. So IQR is Q3 minus Q1. So what is the value of Q3? So Q3 is 33.45 minus 27.3. So that gives you a value of 6.15. So that is the IQR. Now let's take the first observation into consideration. So x less than Q1 is 27.3 minus 1.5 times IQR is 6.15. So let's find this value. So that gives you 18.075. So if there is an observation that's less than 18.075, that's an outlier. In the same way, let's try to find the second one where we are taking in x greater than Q3 is 33.45 plus 1.5 times 6.15. So x greater than, so again 6.15 times 1.5 plus 33.45. So that gives you a value of 42.675. So if any value is here, this is an outlier also as well. Let's look at the data again and let's see where the outliers are. So in this data we are looking at two values, one x less than 18.075, in this the observation here. So notice the first observation is 14.6, so this is an outlier. And notice the higher value, anything greater than 42.675, notice this value, this is also an outlier. So there are two outliers, so 14.6 and 44.0 are outliers, right? So finding the outliers gives you a specific understanding of trying to adjust the interquartile range to as smaller value as possible and as close to the original value as possible. So this is how we find the actual value of the interquartile range and the outliers. Next, let's find kurtosis. What is kurtosis? So kurtosis is the measure of the degree to which a distribution is peaked or flat to a normal distribution whose graph is generally characterized by a bell shape. So what does that mean? If you take a general normal distribution, so normal distribution is where symmetric, which means there is equal part on both sides. So there is a bell shaped curve, there is a constant up and a constant down. Now the chances are all the data in general are not the same way. So this is a normal bell shaped curve of a normal distribution, but all of the data generally cannot be that way. So if a distribution possesses an excessive proportion of observations in its tails, so that its graph exhibits a flattened appearance, so we call that a platykurtic system. So what is a platykurtic one? For example, if you have a lot of observations on the tail, so then this is an example of a platykurtic distribution. So we call the normal distribution mesokurtic distribution. So we call this a mesokurtic distribution, and this is a platykurtic distribution. The other one is if there is excessive values at the mean and it's too peaked, right? If there are less values on the tail, so here there are more values on tail and looks flattened. Here there are more values at the peak and less on the tail, so it looks tall or peaked. This is an example of a leptokurtic distribution. This is an example of a leptokurtic distribution. Right? If it's too peaked, then that is leptokurtic. If it's too flat, then it's platykurtic. If it is a normal one, the normal is mesokurtic. So these are the three ways we can distinguish the observations. So if you have a small proportion of observations in its tail and graph exhibits a more peaked appearance, we call that a leptokurtic distribution. So one way of differentiating it by using a value of kurtosis. So this is the formula. You don't need to know the formula, just remember that a perfect mesokurtic distribution has a kurtosis measure of 0. So kurtosis measure is nearly equal to 0 for mesokurtic distributions. So if kurtosis is less than 0, so that's a platykurtic distribution. For leptokurtic, the measure of kurtosis is greater than 0. So this is how we can find the actual values of these observations. So most of these kurtosis measures are generally calculated by using a computer algorithm, but this is a common sense way of actually finding the distribution and how it looks like. So this here is an example. Notice the mesokurtic, there is an equal distribution of data throughout the entire distribution. But if you took at a leptokurtic, there's too much at the peak but too less at the tails. But in a platykurtic, it's much more flattened. So it's much more of a flattened distribution. So notice the kurtosis measures. So mesokurtic is nearly 0 for platykurtic is generally negative. So this is how we can find the actual values. Next, let's talk about an ordered array. So the first step in organizing data is to prepare an ordered array. So an ordered array is basically a listing of the values of a collection. You can have either a population or a sample in the order of magnitude. So from the smallest value to the largest value. So if the number of measurements are to be ordered, then so to order variables of any appreciable size, so the use of a computer to prepare the ordered array is generally highly desirable. So an ordered array basically enables one to determine quickly the value of the smallest measurement and the value of the largest measurement. Right? So for example, this is an example of an ordered array of ages of given subjects. So here we are starting from the smallest value of 30 to the largest value of 82. So this is an example of an ordered array where we are trying to readily note about 1/3 of the subjects are 50 years or younger. Notice that only these number of people are 50 years or younger. Most of the observations are above 50 years. So this is how we know the usefulness of an ordered array. But all the time ordered arrays are not useful, because ordered arrays, if the data is too large, it can have a lot of problem in understanding how the data actually resembles. So one way is by grouping data. Why do we group data? Is because we want to summarize the data. Remember that the process in the research studies. So we talked about analysis. So we talked about the measures. Now we are trying to summarize. So summarization is a way of making it easier to determine the nature of the information. So when you group the data, so it provides an overall picture of the unknown population. So when data can be grouped into non-overlapping contiguous intervals. So we call these the class intervals or bins. Right? So class intervals are generally also used to sort data and generally are dependent on the range of the data. Now, how do you know? So there are three things that are questionable here. One is how many number of intervals should I make the data into, and what is the width of each interval? So these are the questions that we generally have. Depending on the number of intervals is a rough rule. There is no fixed rule that this has to be followed. One way of doing it is to take the square root of the sample size. So that is under root n. You can place it, that becomes the number of class intervals, or we can use another formula called the Sturge's formula, which takes into consideration the logarithm value of the sample. So 1 plus 3.322 times log base 10 n. So where k here stands for the number of class intervals and n here is the number of values in the data set. Next, class intervals are generally should be of the same width. So, but sometimes this is impossible to accomplish because you cannot have all the data of the same width every single time. So the class width may be represented by dividing the range by the class interval. So width is represented by range divided by k, where remember that r is the range and k is the number of intervals. So for example, let's say if the range is 100 and if you have a total of 10 class intervals, then the width of each interval is 10. Or let's say if the range is 200 divided by, let's say the total number of intervals is 5, then we can divide each of them into a width of 40. So this is how we know the actual way of splitting the data into its own intervals. Next, let's talk about frequency distribution. So frequency of a particular observation is the number of times the observation occurs in the data. For example, let's say I have a data that says 1, 2, 2, 2, 2, 3, 3, 3 and 4. So how do you find the frequency of each of these values? Is 1 occurs 1 times. So the frequency and the observation. 2 occurs 4 times. 3 occurs 4 times. 4 occur once. So frequency is the number of times that you see a particular value in the data. So that number of repetitions is what we call the frequency of the particular distribution. So when you draw a frequency distribution, is basically an ordered display of each value in the data set together with its frequency, that is the number of times that value occurs in the data set. So important characteristics of large data can be easily accessed by first grouping the data into different class intervals and then determining the number of observations that they fall into. For example, you cannot go out and calculate the number of people who are exactly of the age 21 or exactly of the age 22 or exactly of the age 25 or any other age. So, but what we can also do is we can classify people based on their age by using a class interval. One of those examples is, for example, say a neonatal. What is the neonatal distribution? So neonatal is the number of children who are aged less than 29 days. For example, infants are people who are less than 1 year old. Next, you can say children you can say consider you can consider infants again you can consider until 5 years. For example, total number of people who are aged less than 5 years. You can take the example of adolescents are people aged between 10 to 19. The same way you can take teenagers are generally people who are aged between 20 to 25. You can take adults are generally people who are above 25. This is the idea behind the topic of distributions and why intervals can help under distribution of a data, because exactly choosing a particular value cannot be always good for observing the data. For example, if you take a look at the data on smoking and we might see a large amount of people that are focused between 40 to, so let's say for example the high risk population in let's say coronary heart disease is generally people between 50 to 60, then we know that 50 to 60 age can be the main interval. But if you take exactly the people's age only, for example 51, if the age 51 has 2% risk or 52 has 2% risk, so like this it becomes much more complex. To make it easier, we generally use frequency distributions to make the data much more easier to be accessible. So class intervals here are units of equal width that include all the data from the lowest value to the highest value. So whenever you use them, each data element is placed in its correct class interval. So the number entries in each class are added to give the frequency. So we call this the frequency distribution, and we generally draw a frequency histogram or a frequency polygon. to show the distribution of the data based on the class intervals. For example, let's take the ordered array of the age of subjects that we have taken. So here we have taken this into 6 intervals: 30 to 39, 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89. We are going to count people who are between 30 to 39. For example, you take the data. So these are the people who are between 30 to 39. Next, you are going to find 40 to 49. For example, here you are going to take the data until the people who are between 40 and 49. That's it. Next, you are going to find the data between 50 and 59. So you are going to take people who are until 59. So we can consider all these people under that data set. So, and count each of the observations. That count gives you the total observations in that. For example, 50 to 59 there are 70 people, 40 to 49 there are 46 people, and 30 to 39 there are 11 subjects. In the same way, 60 to 69 there are 45 subjects, 70 to 79 there are 16 subjects, and 80 to 89 there is only one subject. This is one way of determining the frequency distribution, or this here, this is an example of a frequency distribution. So it helps in classifying the data and splitting the data into equal parts so that it's easily accessible for analysis. So the same way we can split it here as well. So the reason we do this is to make sure that we do not take one value into another interval. For example, you can write less than or equal to less than, and less than or equal to less than, which means that any person that's 69.5 will come into this interval rather than going into the first interval. And the same way, any person who is 109.5 will come into this interval rather than going into, so this interval rather than going into this interval.